Hello everyone. Today we are going to do hashed Mac and cipher-based Mac. Okay, it's very simple. We already saw how message authentication codes are generated. We're going to look at these two different types of message authentication codes. Okay, it's very simple. Okay, now what is hashed Mac? It's the Mac itself is going to be generated using some hash function. Okay, so the notations that we are going to see in these slides are, we've seen all these notations before. So H is going to be the hash function, for example, either SHA or MD5 or some hash function. IV is initial value, which is to be inputted to the hash function. M is the message whose hash function is supposed to be calculated. And if this M does not satisfy the block size of the hash function, then padding will be done. So the M will be the actual message plus the padding. Okay. Next, we are going to look at the notations that we will see in the Hmac algorithm. Okay, so YI, the message itself is going to be divided into a number of blocks. Okay, so YI is the ith block of M, and there will be L such blocks, which is going to range from 0 to L minus 1. L is the number of blocks in the message. P is the number of bits in each block. N is the length, that is the output, hash, the length of the hash code. Okay. Now, K is a secret key. And the recommendation is that the length of the secret key must be at least N. That means whatever is the requirement for the length of the hash code, at least that much should be there for the K, the recommended length of the secret key. If the key length is greater than B, B is the number of bits in each block. The key is input to the hash function to produce an n-bit key. Okay, so if it is bigger than what is there for the number of bits, then it will be put through the hash function to get a n-bit key. Now, what is K plus? This K padded with zeros on the left so that the result is B bits. To get B bits, the secret key will be padded with zeros on the left. That is K plus. Okay, so then what we have is two padding values. Input is padded using 36, hexadecimal 36, that is 00110110. And it is repeated as many times as possible, 8 times. Okay, if repeated, B divided, that is the number of bits divided by 8 times, because there are 8 bits over here. Okay, and O pad is output pad, which is 5C, and the bits values are 0101 1100. Okay, this is also repeated B by 8 times. Okay, now we're going to have seen all the bits and pieces of the algorithm. Now we're going to look at the actual algorithm. First step is append zeros to the left end of K to create a B bit string K plus. Okay, so if K is of length 160 and B is 512, then 512 minus 160, 440, 440 bits will be added. Okay, so that is 44 bytes. Okay, then bitwise, second step is bitwise exclusive OR the K plus with the iPad. So whatever is the size of K plus, iPad also must be that size to produce B bit block SI. So the output of the second step is SI, and this SI is going to be appended to the message. Okay, we're going to see the diagrammatic representation, so you will get more details when you look at the diagram. Then you apply the hash function to this message and SI, message appended with SI. Okay, so we get a hash of the output of 3 in 4. Okay, after that XOR K plus with O pad to produce B bit block S0. Earlier it was Si, now it is SO. Si is S input and SO is S output. Okay. Append the hash result, that means the hash result from this step to SO, and then to that total apply the hash H again to the stream generated in this S6 and output the result. This is the final hash value. Okay, we're going to look at the diagram. Look at how it is done. So you can see over here, first K plus is XORed with iPad and the output is SI. This SI is appended to the message and the hash of that particular message with IV n bits is initial value n bit is got. So we have the hash of SI appended with M. Okay. Now here the next step is K plus is XORed with OPAD and we have a B bit input SO. This is appended with the previous hash value and this whole message is once again hashed. And this is the final hash value. Okay, so this is Hmac K, M. Did you get that? That is what we saw in the 7 steps earlier. Now, note that the XOR with iPad, when you do XOR with iPad or XOR with OPAD, the result is half of the bits in K is flipped. Becomes, if it was earlier 0, it will become 1. So half of the bits is flipped. Similarly, when you do XOR with OPAD, again, half of the bits is flipped, but a different set of bits with when we compare with the iPad. Okay, not the same bits are not flipped, a different set of bits are flipped. Okay, in effect, by passing SI and SO through the hash algorithm, we have a pseudo-randomly generated these keys. SI and SO are pseudo-randomly generated 2 keys from K. Okay, so by using iPad and OPAD, 2 different keys from the same K value is generated. Okay, Hmac should execute in approximately the same time as the embedded hash function. So if we are using SHA-1, then the extra steps does not cost too much time, because mostly we are simply doing XOR operations. We're not doing anything else. Okay, XOR and append is the only thing that we are doing. So the approximate time is the same as the SHA, whatever hash function we are using. Okay, Hmac adds 3 executions of the basic hash function. That is, first you see that there is a hash function for SI, SO, and the block produced from the inner hash. So basically, there are 3 executions of the basic hash. Just let's look over here. Okay, so you can see over here, first, there is a hash for this particular value. And then after it has been appended, this hash value, there is a value for this also. Okay, so basically there is only in this particular, before that, to get SI and to get SO, the K plus and all that must be done. That is a different step. Okay, so there are basically 2 hash values, not 3. Then security of Hmac. The appeal of Hmac is that the designers have been able to prove an exact relationship between the strength of the embedded hash function and the strength of Hmac. Okay, so if the SHA function is strong, then there is a good, an exact relationship between the strength of the hash function and the Hmac function. Okay, next we are moving on to cipher-based Mac. This is very simple. The only difference is, instead of using a hash function to generate the Mac, an actual cipher, okay, like either AES or DES or something is going to be used for the creation of the Mac code. Okay, so message authentication code is a technique that involves the use of a secret key, one secret key, to generate a small block of data known as message authentication code. And this is appended to the message. See, we saw this earlier. If we have this message, what the Mac algorithm does is that this message is the input, and from this message, a Mac is generated. Now, this Mac algorithm can be any particular cipher. Okay, and then when it is sent, this message is appended with this MAC value and it is transmitted. On receiving the message with the MAC value, on the receiving side, once again, the message is sent through the MAC algorithm with the same shared key. The MAC is generated and the received MAC and the generated MAC are compared to check whether there is any alteration in the original message. This is what we saw this earlier. Okay, now cipher-based message authentication code, or Cmac, is a message authentication code, that is the algorithm itself is a symmetric cipher. Okay, so it will be either AES or triple DES. Okay, it is specified in NIST standard special publication 800 to 38B. Okay, now message length is an integer multiple of the block size. First, let us consider the operation of Cmac. When the message in Cmac, when the message is an integer multiple of n of the cipher block length, the cipher block length is B, and the message is an integer multiple of n. Okay, so that's what we're going to consider first. In the cipher-based MACs, I told you AES or triple DES can be used. If it is AES, then B will be equal to, that is the block size. We've seen B, we have seen AES and triple DES. So we know that the block sizes are 128 for AES and 64 for triple DES. Okay, so the message is divided into n blocks. So if it is AES, each block will be 128 bits. If it is triple DES, each block will be 64 bits. So the whole message is going to be divided into n blocks. The algorithm makes use of a key, which is k bit. And this key is shared by both the receiver and the sender. Okay, and there is a key bit, k bit encryption key, and an n bit key, k1. Okay, so there is two different keys, one for encryption and one for the key. Okay, for AES, the key sizes can be, we've seen all this earlier, key sizes can be either 128, 192, or 256. For triple DES, the key sizes can be either 112 or 168. Okay, so now let's assume that T is the message, the code, MAC. Okay, also referred to as a tag. That is why it is given as T. And the length of this particular tag is T length. Okay, so tag's length is given as T length, the number of bits of T. Okay, and MSB S of X is the most significant S bits of a string X. Okay, so that is what it means by saying MSB of S of X. The most significant bits of this X, S bits of this X. So the leftmost S bits of the bit string X. Okay, so how Cmac is, cipher-based MAC is calculated. Simple. The first block is encrypted using K. The second block is going to be again encrypted using K, but the previous cipher is XORed with the second block and then encrypted with K. Each time the previous cipher is XORed with the next block and encrypted with K until C of N is equal to the nth block XORed with the previous cipher and XORed with K1, which we saw earlier is another key of n bits. Okay, then this block is encrypted using K and we get C of N, and this C of N is our code. Okay, so MSB, from this C of N we get our MAC. Okay, but the number of bits may be different. So that is why the most significant bits of TLEN, that is that if TLEN is equal to 10, then most big, not 10, it will be multiples of 8. But if it is 10, then the most significant 10 bits is taken as the MAC for this particular message N. Okay, this is the method by which a cipher is used to create MACs. Okay, and this is message length is an integer multiple of the block. Okay, so this is the message length. M1, M2, Mn are the n blocks of the message. They are sent encrypted using the key K, and the first encryption is given to the second encryption, XORed with the next block, and then encryption is done. This keeps continuing till the last block is XORing the next block, the previous cipher, and the key K1, and then they are encrypted. And from this encrypted value, as many bits as is required is taken from the most significant bits, and the MAC is created. Okay, this is what we saw in the previous slide. This is the diagrammatic representation. Okay, now when the message length is not an integer multiple of the block size, it's simple. The last block will be padded so that it can be an integer multiple of the block. And how the padding is done is what is important over here. Okay, so the final block is padded to the right. So the least significant bits are padded, but the first bit will be 1, and then all the other bits, the filling will be with zeros. Okay, so that is how padding is done in cipher-based MAC. The Cmac operation then proceeds as before, except that a different n-bit key, K2, that is, if the size is an integer multiple of block, then K1 is used, otherwise K2 is used. Okay, to generate the two n-bit keys, the block cipher, now K1 and K2 are generated from the values that we already have. So the block cipher is applied to the block that consists entirely of 0 bits. Okay, so K1 and K2 are generated from a block of 0 bits. Okay, the first subkey is derived from the resulting ciphertext. The first subkey is created from the block that we are going to use as input to generate K1 and K2. Input is a 0-bit block. Only zeros are there, 0-bit block. But how K1 and K2 are generated, that is what is being said over here. The first subkey, K1, is derived from the resulting ciphertext by a left shift of 1 bit and conditionally by XORing a constant will be XORed with the left shift of the ciphertext, and it will depend on the block size. Okay, so first the 0 block is given to the cipher and we get the output ciphertext that is left shifted by 1 bit and XORed with the constant, and that output is going to be K1, and the whole thing will depend on the block size. Okay, and the second subkey is derived in the same, that is, the steps are the same, but the subkey, it is not a 000 bit. The first subkey, K1, is given as input to the encryption. Its ciphertext is got as output, and then that ciphertext is left shifted by 1 bit and XORed with a constant to get K2. Okay, so this is how K1 and K2 are generated. So if the message length is not an integer multiple, everything else is the same. The padding is, the first bit is 1 and the rest are zeros. And then everything else is the same. Here the last block is going to be XORed with K2 instead of K1. That's the only difference. And this padding and K2 is only difference from the previous cipher-based MAC. Okay, and with this, now the next topic that we have is X.509, which I had discussed earlier with the module 4. Okay, I didn't discuss it. I just told you all to go through it since it's not part of module 4, but it is part of module 5, and I will be discussing it in the next class. Thank you so much. Now, if you have got any doubts, as usual, please feel free to contact me, and don't forget to like and subscribe. Thank you so much. Bye-bye.